Our first session is on sensor applications, which is an increasingly important topic in our field as sensors play a critical role in monitoring, data collection, and driving technological innovation. To guide us through this session, we have Dr. Jessica Sudden, co-founder of the Institutional Architecture Lab, who will be moderating the session. Dr. Jessica is a senior fellow and director of the This Family Initiative on Environment and Global Affairs at Yale-Jackson School of Global Affairs. She is also a co-founder of the Institutional Architect Lab. Her work on environmental governance focuses on how new sources of data can be leveraged to enable new and more sustainable ways of interacting with the environment around us. Her career in India and US spans academic, program leadership, and strategic advisory roles focused on institutional design for integrating science into policy and social initiatives. I will now hand it over to Dr. Jessica, who will introduce our speakers for this session. Please join me in welcoming Dr. Jessica to the stage.
Thank you very much. So I'm just going to say a couple of words and then introduce the panelists, and we'll get started right away because it's a great group of people and we're starting a bit late. One of the things that always comes up, the title of the panel is Sensor Applications, and one of the questions that I always ask and have actually asked the panelists to reflect on is on the impact of the information that comes from using low-cost sensors in this way. How does the information either motivate or enable some kind of change in the actions or the outcomes related to cleaner air? Information is incredibly powerful, not just for guidance, what to do, what are the pollutants, not just for accountability, holding leaders accountable for enforcing standards and enacting standards, but also for enabling new kinds of institutions. Without high quality source attribution enables regulatory action, being able to track the differences in pollution from one year to another, or the being able to identify pollution around a school, or differences, very, very local differences between one side of the street or another, also facilitates collective action. So in light of that, I think as we go through the different presentations that are about to come, just keep in the back of your minds, and we'll have some time for questions in the end, how can these kinds of applications be scaled up, be replicated, be moved elsewhere, and also be made more powerful in the sense of actually delivering and motivating cleaner air for more people. So without further ado, I'm just going to introduce Dr. Carl Mollings, Assistant Research Scientist, NASA Earth Science and Applied Sciences. He will be speaking about a report that the WMO, that he was the convening lead author on, that the WMO came out with on applications of low-cost sensors as part of a larger constellation of information. He's going to be delivering his talk as a pre-recorded session. He is online and will be available for the Q&A. So we can turn it over to Carl. Thank you.
Good morning, everyone. To begin this session, I'd like to provide a brief overview of a report I was involved in preparing for the World Meteorological Organization's Global Atmospheric Watch program, which is entitled Integrating Low-Cost Sensor Systems and Networks to Enhance Air Quality Applications. To briefly summarize some of the key points from this report, we found that despite remaining technical challenges, low-cost sensor systems, or LCS, represent a key tool for filling gaps in global to local air quality information and contributing data for policy-relevant air quality products. The report summarizes the methods that use low-cost sensor data from networks with tens to hundreds of sensors and combine these data with other information sources to provide deeper insights into the causes and consequences of poor air quality. The known limitations of low-cost sensors data should be accounted for explicitly when applying these different application methods. Finally, we emphasize that low-cost sensor networks require sustained physical and cyber infrastructure along with technical capacity and community involvement to make effective use of the data and produce societally relevant impacts. I want to acknowledge the many authors, contributors, and editors who participated in the drafting of this report, who are listed on the slide here now. In the next several slides, I'll go through the 11 chapters of the report and talk about the key points and takeaways from each chapter. Chapter 1 provided the objectives and the motivation for creating this report. While previous reports by the World Meteorological Organization and others have focused on the assessment of low-cost sensor data quality at an individual unit level, in this report we want to move beyond that to look at the assessment of low-cost sensors at a network level and also how these networks can be integrated with other sources of information to better support various applications in air quality assessment and analysis. Chapter 2 provided an introduction for the different information sources we consider in this report, including, of course, low-cost sensor systems, and also situating low-cost sensors within the wider system of air quality information gathering and analysis, which also includes regulatory monitoring systems, RGM, as well as satellite remote sensing and modeling from the local to global scales. We also talk about the advantages and limitations of each of these data sources and how they can be used together to cover various temporal and spatial scales, as illustrated in the figure. Chapter 3 deals with air quality reconstruction, that is, predicting the air quality at locations other than those directly observed by, for example, the low-cost sensor network. We cover a range of different methods for performing this reconstruction, from simple interpolation techniques to statistical mapping methods and to data assimilation and bias correction of air quality models. Across all these techniques, we find that low-cost sensors, and specifically the increased spatial density facilitated by these lower costs, allow for better performance and better spatial reconstruction across these techniques in most cases. Chapter 4 deals with source identification and attribution. That is the assessment of the contributions of different sources to ambient air quality. Again, we find that the increased spatial density facilitated by low-cost sensors enables the better identification of local sources of pollution. Furthermore, multi-pollutant low-cost sensors, that is, low-cost sensors incorporating detectors for various categories of particulate matter and trace gas pollutants, allow for the application of factorization techniques, such as positive matrix factorization, to identify the specific fingerprints of different pollution sources and sectors. Finally, low-cost sensors can cost-effectively support the evaluation of mitigation activities to reduce the impact of specific sources or sectors. Chapter 5 deals with air quality pattern and trend analysis with a specific view towards environmental justice applications. In these applications, establishing high inter-unit consistency or precision between the low-cost sensors is especially important, as well as establishing long-term stability in performance for trend analysis. Furthermore, combining low-cost sensor data with independent information sources, for example, the increasingly high-resolution satellite remote sensing data which is becoming available, can help to mutually corroborate disparities identified by either data source in isolation. Finally, we emphasize that community involvement in the low-cost sensor network design, deployment, data collection, and analysis is really essential to support the performance of these low-cost sensors, as well as to provide support for long-term mitigation strategies based on the data that these low-cost sensors collect. Chapter 6 deals with health studies and personal exposure modeling. We note that a lack of in situ data is a critical need in many areas to support local epidemiological studies, and this is an area where low-cost sensors can begin to address these data shortcomings. There is a need for better assessment of the long-term performance of low-cost sensors, especially long-term quantitative biases to support those applications. However, we do identify that low-cost sensors data combined with other information sources can effectively facilitate more spatially focused, and short-term health studies in a cost-effective way. Furthermore, the qualitative data and insights from low-cost sensors can help individuals take action to reduce their own personal exposure and mitigate their health risks. Finally, we note that ensuring the privacy of health-relevant information collected by low-cost sensor data is a continuing concern. Chapter 7 deals with air quality forecasting, that is, prediction of near-future air quality based on present and past information. Here we note that low-cost sensors have a particular niche in supporting short-term and localized forecasting in conjunction with more regional and global air quality forecasting models. In these applications, characterizing the uncertainties of low-cost sensor data are especially important in integrating them properly into model forecasts, and also for evaluating model forecasts, particularly in regions where regulatory networks for forecast evaluation are lacking. Overall, we note that the data latency, data quality in terms of accuracy and uncertainty, and the spatial representativity of low-cost sensor networks are key factors in supporting air quality forecasting integrating low-cost sensors. In Chapter 8, we move on from discussions of specific applications to more general considerations which cut across a variety of different applications. The first of these in Chapter 8 are data quality and disclosure concerns. The key point to emphasize from this chapter is that the evaluation of low-cost sensor data quality, including the metrics used in this evaluation, should always be based on the air quality management decisions which these data will support, and evaluation should mimic the intended use case of the data as closely as possible. So, for example, if low-cost sensors are going to be used to support prioritization of interventions based on which areas have, for example, the worst air quality problems based on a particular pollutant metric, then assessing the performance of the low-cost sensors in terms of their ability to identify where these problem areas are, for example, the inter-unit precision of the low-cost sensors, or the ability of low-cost sensors to correctly identify spatial disparities in exposure, are the relevant performance metrics which should be evaluated, as opposed to other metrics like, for example, the exact quantitative bias of the individual sensors, which are less relevant for that particular use case. In all cases, however, well-defined and transparently reported methods should be used, and metrics should be reported in a standard way to enable easy assessments and comparisons of performance between different evaluations. Chapter 9 deals with air quality monitoring network design. Again, this needs to be guided by the intended use case of the data and the specific role that the low-cost sensors will play in the context of a wider air quality monitoring system. In this chapter, we discuss a few common use cases for low-cost sensors in network design. These include exploratory analysis, expanding upon an existing network, supplementing an existing monitoring network for a specific area, and providing emergency response deployments in response to, for example, a natural disaster. It's also worth emphasizing again that low-cost sensors are one of the many available sources of air quality information that needs to be considered when designing an air quality monitoring system. Chapter 10 deals with the infrastructure necessary to support effective applications of low-cost sensor networks. This includes the physical infrastructure, which is, of course, the sensors themselves, any necessary equipment and spare parts to maintain the sensors, suitable locations for siting the sensors, as well as power and communications connectivity. Cyber infrastructure required for these networks include systems for data storage and processing, and this should also include common formats and standards for the data to enable accessibility and interoperability. And this is an area where national and international organizations can play a role in guiding and creating standards that can be followed to ensure this accessibility and interoperability of air quality data. These networks also require extensive technical capacity. The operators and managers of the network need technical training both in the sensors themselves as well as the data analysis techniques for interpreting the data. And this can be facilitated through the sharing of best practices and guidances nationally and internationally, which is one of the main focuses of this conference that we're at now. And finally, this should also include public outreach, and this includes educating decision makers and policymakers about the advantages and also, of course, the limitations of low-cost sensor data. And finally, all of this requires financial and institutional support, so sustained funding sources and involvement of relevant government bodies as well as the communities to really enable and sustain pathways from the data collected by low-cost sensors to actions taken to mitigate poor air quality. Chapter 11 summarizes the best practices for integrating low-cost sensors. So to summarize, these can be useful tools for acquiring air quality pattern and trend information. In regions lacking regulatory monitoring, LCS can provide the first insights into local air quality and guide further investigation and prioritize mitigation strategies. Whereas in regions with existing regulatory systems in place, these low-cost sensors can supplement these regulatory networks with increasingly localized and near real-time data. Assessing performance in the target environment via co-location with regulatory monitors is still the recommended best practice wherever possible to support any quantitative application of low-cost sensor data. And when this performance is appropriately accounted for, as we show throughout the report, these low-cost sensor networks have great potential to enhance a variety of air quality applications, including spatial reconstruction, forecasting, source identification, and health and environmental justice applications. Finally, sustained and attainable funding is needed to support low-cost sensor network design, deployment, management, data storage and analysis, and finally, of course, translating the low-cost sensor data into insight and eventually into action. So thank you very much for your attention. If you want to read the report, it is freely available on the World Meteorological Organization website at the link listed here. Thank you very much for your attention.
Thank you, Carl. I would encourage everyone to take a look at this report. It came out of some work of the Global Air Quality Forecasting and Information Systems Working Group within the Global Atmosphere Watch that Subbu is on, and I co-chair the committee, but it came out of our efforts to increase the supply of useful observations and the recognition that the previous two reports that the WMO had done had looked only at LCS data as data points, but not in the kind of constellations of information that are important for services such as forecasting and source attribution. And Carl did an amazing job at bringing together inputs from authors around the world, I think something close to 45 authors. So our next speaker is Dr. Sarath Gutikunda, who probably needs no introduction in this crowd. I had described him earlier this morning as the OG of air quality, information, emissions inventories, outreach, education to all levels. But he will be speaking about, he is the founder director of Urban Emissions Info and an adjunct professor at IIT Delhi. He'll actually be speaking about complementary ground monitoring with emissions and pollution monitoring in Kampala, Uganda, exactly the kind of constellation of information to provide insight and policy relevant insight that we're hoping with the WMO report to encourage and elevate and attract funding to more of. So over to you, Sarath.
Thank you, Jessica. That was a generous introduction. I'm sorry that Dio Kure couldn't come. He was supposed to present this work. He would have been talking a lot about the sensors. I don't do not much of work on sensors. I do a lot of modeling work, and we have complemented each other's efforts. So my presentation today will be more on the lines of how do we complement the monitoring work that's going on the ground and try to understand what's happening in those lines that you get from the monitoring data. So AirCo, they started in Kampala, but they have been working in a lot of other countries as well. As you can see from the map, within Uganda, they have expanded quite a bit, and now they're working in about 15 African countries. In Kampala, they have about 63 stations running right now. All of them are low-cost sensors, co-located with reference grade stations at the university and at the US Embassy station, and they build the calibration curves and things like that. And they have a web platform where you can download the data, and they also have apps where you can browse a lot of information from, not only from the network, but also other information coming from other networks and studies. if anybody here who attended Soumya's and Garima's presentation on a training event on Monday, you will know that the data that you get can be presented in many ways. One of them is like this, very messy lines from every station that you have, that you can see the ranges. As you can see, that's the pattern that you have in each of the sensors is very similar, but there are the heterogeneity among the stations is very strong. So it basically tells you that within Kampala there are a lot of features in the emission features and a lot of sources that are there that needs to be worked on, and what can we learn from that part of the story. So this is more of a cleaner version of the same plot. Basically tells you month by month what are the ranges of the pollution that we are seeing across the city and what are the averages that we are looking at. Generally speaking, the annual average is about 50 micrograms per meter cube. It's about half of what we usually see in Delhi's numbers, but it's still, in terms of exposure, in terms of health impacts, it tells a lot of, it tells a big story. The trends are very similar to whatever you find, especially, for example, if you go to March, April, the numbers dip because that's the rainy season. They have very heavy rains during those 2 months, so it fills the pattern quite well. And the diurnal cycle, I mean, no surprises there. We have a morning peak, you have an evening peak, and then the evening peak sustains for some time because of the inversion layer kicking in, and then the pattern follows the next day again. Now, this is how many of you were there at the training event on Monday that I've done? Okay. Cool, so some hands are still there. So this is the part of work that we were trying to show in the training. So you can do a lot of monitoring work. I mean, you can run 60 stations, you can draw all these lines, but how do we, like, what can we learn from it? So that part will happen only if you do some bottom-up emissions and pollution modeling work. Okay, then that will help us build an application, that will help us trying to explain why are those highs happening, why are the lows happening, if there are any discrepancies, what can we explain, how can we explain those discrepancies with whatever we have, the kind of information that we have. So for Kampala, this is the airshed that we have defined, about 60 by 60 grids, and a lot of open sources are available that can be used to pull a lot of information. So one of the portals is this OpenStreetMaps, where we've used that to build a road network information. So you have the primary roads, secondary roads, arterial roads. You can pull in as much information as possible, and they have a lot of metadata on these roads as well that can be used as proxies for some spatial allocation. So these are the things that we discussed at the training event, but this is an application of that. The same resource can also be used to pull up a lot of the commercial activity density in terms of hotels, hospitals, malls, markets, industrial estates, apartment buildings. So all that is very useful in trying to understand where are the hotspots. And if we have to concentrate our efforts in any of the locations, then where will be our biggest bang for the buck? You know, where are the hotspots and how much can we do in reducing the emissions of pollution in those areas? Okay. And there are a lot of other resources as well. One of them is European Space Agency's global human settlements work. So they have now from 1975 to 2020, 2025 projected numbers on how the urbanization is increasing in various cities. It's a really good metric to use for multiple reasons. So one, the urban development, urban built-up area change is a proxy for us to look at the demand for commercial amenities. So the urban area increases, then there is a lot of demand for traffic, the mobility, there is a lot of demand for electricity, there is a lot of demand for residential cooking and heating needs, and also the commercial amenities themselves. Like you need more hospitals, more hotels, more apartment buildings are coming up. So all of them are energy sinks. Okay, so we can actually use how that trend is coming, is increasing, and what can we learn from that. So this is one of the satellite products. So it doesn't tell you exactly what the energy demand is, but it tells you a trend. So we can actually use that in trying to explain some of the stories. The right side of the plot is the road network maps from the OpenStreetMaps. Then what we also do is scan through the entire airshed, trying to find any sources that we can't account for in already existing literature. Okay? So in general, if you go to IEA, the International Energy Agency, they publish some numbers on the energy consumption for the country. For some cities, they have some specific numbers. So but it only gives you some coarse numbers. But we need a lot more specific localized numbers for the cities. So we do a lot of this scanning work so we can understand what's happening in the city itself. The very first figure is actually the Kwangi power plant. It's a heavy oil power plant. It's about only 50 megawatts. Most of the energy needs in Kampala and Uganda are driven by biomass and charcoal usage, both at the industrial level and also at the residential level. The oil usage is only about 10%, the energy needs for the oil for the energy needs. There are also two other cogeneration power plants, but that's only used pretty much in the industries themselves. There's a cobalt plant, quite big. They have about 10 megawatts of cogeneration. There's a sugar plant. They have a 7.5 megawatt cogeneration that's happening. That sugar plant is basically, as you can imagine, they basically use all the waste from the sugar factory, so all the biomass-driven exercise there. Second figure is a cement plant. It's a 1 million ton capacity cement plant. That's huge. That plant uses most of the coal that comes into the country, at least in the city airshed. So it's a big black spot that you'll see in the map. The third image is actually the Kiteji landfill. It's 0.15 square kilometers, what's marked there. It helps us to understand how much of the waste is actually going to the landfills. It's about 50% of the processing capacity of what is actually generated in the city. So city has a generation rate of about 1,400 tons per day, and the landfill has a processing capacity of 700 to 800. So which means that a good chunk of it is actually left behind, means that there's a lot of open waste burning that happens across the city that you will see. The bottom four panels, they're all quarries. They're very unofficial. You don't find a lot of documentation of these, and they're spread across the airshed. These are rock quarries, means a lot of rock crushing and processing happens, and all that is then shipped to all the construction activities that are happening in the city. So all these scanning work is important because these are the sources we have to identify. I mean, these are not the regular sources that you will find in the city that can be immediately used. Okay, the regular sources like transportation. Okay, so this is first thing that comes to our mind. What's polluting? What is increasing those numbers? It's basically transportation. So your congestion problem is very high. Most of the traffic, if you look at the traffic mix, it's very different from what you will find in the countries like India or even in China. In fact, like 46%, 50% of the traffic is moved through these 14-seater buses here. It's not the personal transportation modes. Actually, when you can't call them public transportation, they are semi-transportation modes, but they do contribute a lot to the traffic congestion and of course they contribute to mobility as well. And a big chunk of these vehicles are second-hand. The second-hand market is very strong, which means that when we may be having a BS6 or BS4 vehicle, Euro 4, Euro 6 vehicle, but there the standards are still, the on-the-road standards are still Euro 1, Euro 2, and they pollute quite a bit. And we put all that together. We have a emission inventory map that combines the meteorological fields and all the information that we have collected from the activities. And a lot of this information is online. All the emission inventories that we have built for all the sectors, even the point sources, it's all on Zonedo. You can download them. They are model ready if you want to use them in a model right away. We use the WRF-CAMX system. Again, it's a very standard process. We run through that, and then we have a heat map that you can see. But most importantly, what we are trying to do is trying to complement this modeling work with the monitoring work. Are we able to replicate what we are seeing in the monitoring stations, and what can we learn from it? If we are not able to replicate what we are seeing in the models, then we can't use this information for any of the scenario analysis. So this is where we go a little back and forth on all the sources that we have mapped and what can we go from it. Generally speaking, we were able to match the qualitative and quantitative trends in the both in the modeling data, but again, it's a learning process. this is the first time it's being done in Kampala, so and then a lot of resources have been put together for the very first time, and we'll go back and revisit that. So one of the things that really popped up in the model is the source apportionment numbers, especially in the Jan and Feb. You will see that Jan and Feb actually jumps up quite a bit compared to all the other months. And we wanted to see like why Jan and Feb are so high in general. Given the temperature profiles are very normal across the months, they have a really good weather, so there's no heating component that kicks in the way we have in the northern latitudes in India. So this we could explain only through the boundary conditions. So the WRF-CAMX model, we use the boundary conditions from the global model, Mozart, and if you see that organic aerosols really kick in the boundary conditions, especially in January and February. So the same table for all the other months, it looks at like 5 micrograms per meter cube or 10 micrograms per meter cube max, but for Jan and Feb, we have like 50 micrograms per meter cube. That can be explained through the fire counts that we have in the northern sector. So Kampala is... So we're at 12. We're at 12 minutes. Yeah, I'm almost done. So Kampala is about on the south side, most of the fires happen here. That's about 600 kilometers, enough distance to make a lot of secondary organic aerosols coming from these fires. And if you look at the meteorological fields, a lot of meteorological fields, the average meteorological fields in Kampala, especially in January, February, are coming from the north. So which means that a lot of the long-range transport is happening in Jan, Feb, and the secondary organic aerosols can explain the bump that we see in the total emissions. So I'll stop there. Like I said, this is the first time we've put together a emissions and the modeling work to complement a lot of monitoring work that's happening on the ground, and we're trying to explain both to the people who are working on the ground, and also they are the ones taking these stories to the city officials, and obviously they want to know why are there bumps happening. So we want to explain scientifically what is contributing to those trends. And this is something we'll continue doing this a couple more rounds and see what can we do for the next rounds. So we have similar works happening in Africa for Addis Ababa, Accra, Lusaka, Nairobi, and a few other places, and Bishkek. Inventories are already online on the Zonedo. You can download them. So if you have another model running and you want to run the inventories in your model and see if you can do the same studies, feel free to use them, and please share if you find anything different from what we have. Thank you.
Thank you, Sharath. The theme for this conference is the future of participatory air quality management. And I think one of the things I've noticed over the years is that whenever you see an interesting emission inventory, essentially the picture of the origins of pollution, whenever you see one that is omnivorous, that uses all kinds of different inputs and sources to get a full picture of emissions, Sharath is usually involved with it. So the combination of these kinds of attention to using new sources of data and to get a picture of the origins of pollution with the kind of sensor networks that AirQuo have been creating is, I think, incredibly powerful. So we're going to switch gears a little bit now and I'm going to invite Jason Gu, who is the Chief Technology Officer of Sensit Technology, to join us and to speak a bit about what Sensit is doing with combining these different sources of information to monitor industries. Over to you, Jason.
Hi, everybody. Thank you for the introduction. Does this work? Did this move forward, right? The middle one, and then is there a dot? No? Okay, no worries. Hi, everyone. Thank you for the introduction. I think I wanted to talk a little bit about the work that we've been doing in industrial monitoring, right, and specifically how we've been using low-cost sensors, right, to help with industrial emissions, primarily actually on the other side of the fence, right? I've been hearing all these talks this week about air quality systems and low-cost air quality monitoring devices that are being deployed into cities, and, monitoring the air shed and monitoring the different sources that are present within an urban environment, or, right, we typically do work, and I mean, we do work in that space, right, in terms of the sensor ramp and multi-pollutant monitoring, but we actually typically work on the other side of the fence, right? A lot of our devices are deployed not in the cities, but actually within the industrial complexes, right? And I want to talk a little bit about kind of our experience with deploying those devices, as well as also kind of my experience kind of interacting with those organizations, right, as a scientist and as an academic, and talking a little bit about how it was very difficult, right, to interact with them, to convince them to do low-cost monitoring, to have more data, and what things have worked in the past in terms of what we were able to propose to those organizations that made it very attractive for them to deploy more monitors and to help them reduce their leaks and reduce their emissions. And primarily, I think I want to focus a little bit on really how the community monitoring application is very different from the industrial application, right, and kind of where the differences are, and how do you kind of overcome those differences. So, just to give you a quick overview of kind of the different types of devices we've deployed, right? This is, I think, all the devices that we've deployed in the past 12 months or so. And what you notice is typically air quality monitors, low-cost monitors, whether they're industrial or they're, in a community, they all look about the same, right? It's all just a box with some sensors in it, which is, and you can see kind of varying versions of our boxes, right, that are deployed in different applications out there, right? The first one is a methane detector that is actually monitoring a producing well pad, right? And this picture doesn't do it justice, right? Steve and I were there earlier this year, and when you stand there, you see that like kind of the well pad in the back, that goes on for miles and miles and miles, right? Like when we were driving out of there, it took us about an hour of driving before we left, or rather before we stopped seeing well pads, right? So the scope of these things are incredible, and voluntarily, the company that deployed these devices, they deployed quite a good number of them, and they really wanted to understand their emissions, right, and to be able to find and fix leaks and find the sources of these emissions. So they deployed a few of these devices out there, and we're monitoring essentially the emissions coming out of these wellheads. The picture up there is when one of these wellheads are being drilled. So that big tower there, that's about 3 stories tall, is when they're drilling. That's a drill. And they're drilling into the ground to basically open up a hole so that they can then pull out oil and gas, right? And then as part of that, they drill a hole, then they seal it up, and then they basically put one of these well pads on there, so then they start producing oil and gas and pulling essentially oil out of the ground. And so if you look at the bottom there, there's a VOC monitor of ours right underneath there, and they're actually required by law, right, whenever they drill, to have VOC monitors present to make sure that all the sealing and stuff occurs and there's nothing wrong with the system when they're done. The bottom one down here, I don't actually remember what that one is now that I look at it, which is a little unfortunate, but you can see in the background, this is more of a fence line monitor, whereas the other two are more fugitive emission monitors. But essentially, it's some sort of factory. I think it might be a steel mill. I'm not sure. But it's basically a production facility or an industrial facility of some kind. The picture over there, you can see Steve. He's the guy in the blue flame-resistant suit there. That's a gate station. So essentially, whenever natural gas is being transported to pipelines, right, you're going from a high-pressure system to a low-pressure system when it's being fed to your house. This is a facility where the pipeline is interacting with the distribution system to feed to your homes. And once again, this company is voluntarily deploying these devices because they're concerned about potential leaks in their infrastructure as well as potential leaks in the pipeline. So that they were really concerned about their Scope 1 emissions, and so they deployed a bunch of these devices. The last one actually is a ramp, and it's actually kind of the rare use of a ramp in an industrial application. And I believe this was near a refinery, but it was looking at a agricultural application, right? And you can see how that ramp deployment is quite different from what you would see in a city, right? They have SUMA canisters connected to it. They're using the ramp to trigger canisters so that they can then do compliance efforts. The thing, like if you look at these deployments, right, and you compare these to the sensors that essentially you've seen this entire conference, they look kind of different, right? And so when I look at them, the first difference I can see, right, is the fact that most of the time, these things are not deployed onto fixed assets, right? You think of fence line monitoring, you think it's on a fence, but primarily, these are not, almost never deployed on fences. They're typically deployed on tripods. You can kind of see these tripods, and they put sandbags to make sure that the tripods don't blow over, and they attach the solar panels to the tripods. And the main reason they do that is because they move these around, right? So we always think of it as, you deploy a device, it's sitting there, it's collecting data, and it's never being moved. In an industrial setting, depending on what they're doing at the plant, they will easily move these around to different parts of the plant to answer various questions that they have about the plant. The other thing that I want to make note of here is even with the ramp, all of these will have ultrasonic anemometers on them, right? And so to most of these industrial plants, and especially for fugitive emissions, just the number isn't that useful to them, right? It's how the number of, in terms of measuring how much pollution there is relative to the wind speed and wind direction so that they can help locate where that leak is coming from. So it's much more focused in terms of their scope as opposed to just putting devices out there and collecting data. So, I typically think of emissions as three different things, right? There's one that is in source, that is at the source, right? This is essentially sensors and low-cost sensors that are being deployed within the plant, near compressors, near pumps, right? The second one is fence line applications. So these are devices that are being deployed a little farther away at the fence line. And the last one is community, but I'm not going to talk too much about our work there. Everybody has a slide like this, essentially, just kind of showcases the different products that we have. I want to make 3 points here, right? One is that if you look at the community, you have the ramps, you have these multi-pollutant detectors, right? As you go into the industrial environment, the FMD is a methane-only device. It detects about 100 part per billion of methane. The SPOD is a VOC-only device, right? As you start going into industrial monitoring, you start having less and less multi-pollutant devices and more very focused, very specific instruments that are designed to do one thing and one thing only, right? And they mainly focus on them doing that thing well. They're not collecting data to see as an exploratory exercise, right? To see what else is there. They know they have VOCs. They know they have methane that's being emitted, and they only want to know what's going on with the methane and the VOCs. The other thing I want to kind of point out is if you look at the at source, right, there's the SPOD, the FMD, and then underneath you see C1D2, C1D1. Those are intrinsic safety certifications. In order for you to deploy inside a fence line, you have to have intrinsic safety certifications. And what that essentially says is that we have dangerous environments, things that can explode, right? And your equipment, when you're deployed there, will not cause an explosion. They're fun certifications to get, but they're quite different in terms of how do you build the product, how do you do all these things. And the last thing is really the data, right? We have an own your own data model, and the reason for that is because if you want to interact with an industrial operation, by and large, right, we talk a lot about in the community monitoring space about open dashboards and open source data and open source APIs. Absolutely not possible in the industrial space, right? 90% of the devices that we deploy out there never touches any of our servers, right? They don't allow the device to send data out to our server. They have their own server on premise, and the data never actually leaves the facility. So the only time that we see any of the data is when they have a problem with a device, right? They'll send us like an Excel sheet, and then we scroll through these Excel sheets to help them troubleshoot. And really, the main point I want to make here, right, is a community monitor is not necessarily suited for industrial monitoring, right? And it's almost unfair for you to say, hey, we have these community monitors that we're putting out in the community, why can't the plant deploy them, right? And there's actually really good reasons why they can, and typically, right, what they want from an industrial setting is very different from what, an air quality researcher or a community monitor would want to see. So I really want to make that point across, in terms of building things fit for purpose, right? And even from this side of the fence, right, on the community side, to understand why potentially the industrial plant can't deploy, purple airs, right? Because there's no certifications to them, they might cause an issue in the plant, the additional data might not be helpful to them just to know the number. So I mainly want to highlight kind of some of the work we've been doing with VOCs. There's similar work with methane. Going back to this open data model, when I was looking at putting this presentation together, I wrote the abstract, I submitted it, I got accepted, and then I was like, oh cool, I'm going to grab a bunch of data. And so I emailed some of our customers like, hey, can I share some data in a COC? And the overwhelming response was no. You cannot share anything with anybody, period. So, but I still wanted to give you guys an appreciation for, hey, this is what the industrial plant is doing with these low-cost sensors. This is how they're using the data. This is the value they're deriving, right? And so, luckily, for VOCs, a lot of what the industrial plants do mirrors what the US EPA does. And the US EPA has been very generous in terms of publishing their data in terms of how they use these devices. And so, I'm going to talk quite a bit about data that, from workshops and stuff that is being provided by the US EPA, right? And, okay, I'm reasonably getting there. And so you can kind of see, right, the US EPA deploys these devices. This is once again a voluntary deployment, right, where the plant invited the US EPA in, right, because the US EPA proposed some monitoring, a monitoring project to the plant. They deployed these SPOTs to monitor those tanks. There's a production facility connected to that tank, right? And this is in essence what the data looks like that they're collecting, right? And you guys are all very familiar with this type of data. They typically don't look at average data. They look at raw data on the 1 second, 5 second interval. And what you can see here is, right, this is a PID reading for VOCs, near zero, and then you see these spikes, right? And that's essentially where the plume is being blown into the device, right? And then the wind changes, moves away, so on and so forth, and you can see these spikes here, right? And typically, on some level, a lot of plants just have a device like this deployed near their assets, and they'll set a fixed threshold, right? Anytime this thing goes over some amount, I get an email about it, and then I send a crew out to go fix or to go look at the problems. And a lot of plants do only this. Beyond that, you have what the EPA calls source direction indicator plots. They're basically wind roses, right? And what this is saying is whenever, and that's actually the wind rose plot for this set of data. And what it's really saying is whenever you have high VOC readings, the wind is blowing from the north, which is pretty reasonable. And you can only do this though, right? Because you have discrete points of emission, right? It's not, hey, there's some guys cooking and there's some guys doing this and doing that, and there's a lot of activity there. It's a very focused activity of them doing production, so they know exactly what stuff they have, and their leaks are typically open joints or valves that are leaky, right? So it's very discrete sources that they have, and so you're able to do these types of approaches where, especially in your source, within a couple hundred meters, right? You have, the EPA was deploying one SPOD in Site 1 and one SPOD in Site 1A, and they're able to see from Site 1, you see basically emissions whenever the wind blows from the north, and the other one you see emissions whenever the wind is blowing from the northeast, and you can triangulate kind of where the leak is, right? And I know as air quality researchers, it's extremely tempting when you look at this to go, well, you can build a transport model and you can be much more detailed on figuring out how and where exactly the leak is. We proposed that to a lot of plants. You just see their eyes glaze over, right? They have no idea what we were talking about. And generally, we always talk about capacity building on the nonprofit community side, right? But that's also true on the industrial side. A lot of times they don't know, thank you, they don't know what we're talking about. I think I'm gonna run out of time, but they don't know what we're talking about. And in essence, there's huge benefit, especially when you're dealing with industrial sites, to keep it as simple as possible, right? If they don't understand it, they're not going to adopt it and they're not going to do it. So it's very important that we explain things in a way that they understand. And I get there's a lot of complex and advanced analyses we can do, but sometimes maybe to keep that in our back pocket and to engage in a very simple way, I think is quite important. The next part of it, right, is there. Okay, sounds good. So there's a lot of, there's a lot of other things that they've been doing, but this is some work essentially where they were triggering canisters with these VOC readings, right, in order to get legally defensible data, but also to get speciated data, right? So here you can see no readings, you see a big spike, the SPOT triggered a canister of about a minute long, and they were able to find 637 parts per billion of cyclohexane within that canister. So we help them basically essentially only do lab analysis when there is pollution within their canister, right? So it's quite interesting. And then we also have quite a bit of mobile applications where a lot of plants are now deploying SPODs and FMDs onto cars, and they're driving those cars around. And in the plant, you can see within that map there's oil wells, and you can see exactly that blue dot down by the bottom there is where they saw a spike in the VOC readings. So I think really there's quite a bit of other stuff that is on here in terms of low-cost sensors, but come talk to me afterwards. Okay.
Thank you. I think that was an incredibly important reminder of some of the differences in the specific context in which monitors are going, and also, to some extent, a recognition of the level of collaboration that's possible if you can understand where different stakeholders are coming from. Thank you very much. And we have one more speaker on the panel, and we will still have about 10, maybe 15 minutes for questions at the end. I'd like to introduce Victoria Owusu-Tawiah, and hopefully I have not completely butchered your name. Victoria is pursuing a PhD in meteorology and climate science at the Kwame Nkrumah University of Science and Technology, and her work focuses on evaluating air quality models, developing bias correction tools for forecasting air quality over selected regions in Ghana. She will be speaking about looking at some ways to incorporate sensors and modeling for forecasting. So over to you, Victoria.
Hi everyone, good morning, and thanks Jessica for the introduction. I'm Victoria Owusu-Tawiah, a PhD student from the Kwame Nkrumah University of Science and Technology. My work focuses on evaluating and bias correction of the GeoCF model for PM2.5 prediction in sub-Saharan Africa using machine learning tool. So before the talk yesterday, I decided to look at the stripes from the air quality stripes. The link is up there for Accra, Kampala, Kigali, and Nairobi. This is because that's the focus for the study area for my work. And just so we have an idea of what is going on, we saw that of India, and I thought it wise to just bring this up. Data was mostly collected or data collection was started around early 2000s, and so that's where we could see the clear representation of pollution levels across these cities. Now going forward, for my work, it's geared towards the Canary Alert by the World Resources Institute. And then what is the Canary Alert? What is it all about? It's just about developing a decision tool for forecasting over cities in Africa. However, there's a limitation or challenge with sparse network of data, ground-based data, and so we try to use models to predict the forecast, PM2.5, over these cities. Another limitation to coming from sub-Saharan Africa is the fact that there's not a distinct model developed for our area, and so we tend to depend much on global models, which has its own limitations with regards to replicating or simulating exactly the local effects or the local terrain of an and then environmental conditions of a specific place. So what we seek to do is to evaluate the model, forecasting model, and then try to see if there's any biases with the ground data, and develop a bias correction tool using machine learning to be able to get improved and accurate forecasts over selected cities in Africa. At the end of the day, we seek to scale it up over different areas. So that is the whole idea about Canary Alerts, knowing the quality of air or PM predictions for tomorrow based on today's data. That is what we seek to gain. Going forward, I'll just highlight on the WMO initiative under the Global Atmospheric Watch Program, which seeks to provide globally harmonized air quality forecasts for tailored to specific needs for its users. And so the GeoCF model and forecasting model seeks to make inputs, or it's an effort that is recognized under this WMO program. From previous talk from Monday, have highlighted on the health impact of air pollution, air quality, and then also where sources of various data are gotten from satellites, data modeling, and then even ground-based data. Each data set has its own limitations, and also what we try to do, even with the co-location of low-cost sensors, we try to make it have some good enough data or accurate data coming in from these sensors. However, my work is focusing on using these low-cost sensors and then the model output to improve air quality forecasting over in sub-Saharan Africa. So this is just a simple setup of a simple picture of how a model is set up. It takes into account the local terrain, current weather forecast, chemistry over the specific area, and also it takes into account the emissions over that particular region. At the end of the day, what we seek to get out of developing this forecasting model is forecasting of atmospheric composition or air pollutants over these areas or over the regions we are looking at. And so for my work, like I said initially on the Canary Alerts, we are looking at the GeoCF model, which has been developed by NASA. And then it takes into account the physics, that's the meteorology, and then the chemistry, incorporates it together with the local factors or the terrain and emission. And then we get the GeoCF, the geocomposition forecast at the end of the day. That is highlighted in green. And the GeoCF is one of the few global forecasting systems conducting some of these gaseous and aerosol composition simulations in real time. The GeoCF, I thought Carl will highlight on that, and I'm so glad he's on. The GeoCF has a spatial resolution of 25 by 25 kilometers square, a temporal resolution of an hourly of 1 hour, and then also gives a forecast of specific pollutants such as PM2.5, NO2, SO2, and then ozone. And also it takes into account giving an output of the meteorology, that's temperature, relative humidity, wind speed, and then precipitation as well. Now, so motivation for this work, there's the need for accurate PM2.5 predictions as suggested by the WMO Global Watch program. And so, however, in sub-Saharan Africa, due to lack of data or sparse network of data, we are not able to make that or we don't have reliable, accurate predictions over sub-Saharan Africa. And so it is critical to have this to inform decisions in policy making with regards to air quality management systems, and also to provide some public health interventions as well. However, these model struggles, like I said, each data set has its own limitations. And so with the models, they struggle to capture accurately the local variations since they are global models and have coarse resolutions. So what we seek to do with the Canary Alert is to combine the data from the model and then ground-based model. We use the XGBoost machine learning to correct the bias, and in so doing provide a framework that could be applied to other cities facing similar challenges. And this work I would highlight is based on the work done by Christoph and the NASA team, the developers of the GeoCF model, on the description of the model and also bias correction of the model to help give out improved forecasts. So my study area, the study spans from 2021 to 2022, that's a year data. My study area focuses on these pilot cities, Accra, Kigali, Nairobi, and then Kampala. So that's where we got the initial, what we are having data from. And so that's the pilot cities we are looking at for now. However, it's worthy to know that for Accra and Nairobi, the data we got from the local sensor data, we couldn't use that because we set a threshold of, due to the machine learning, we set a threshold of about 75% consistency in data, but then the data we got from the local sensors had gaps and couldn't meet that 75% threshold. So we relied on reference grade monitor, that's the BAM, in Nairobi and then Accra. But for Kigali and Kampala, we were able to get good enough data from the local sensor ECHO to incorporate in this project. Now for the workflow, we combine data from the model and then the ground-based data, do some quality checks on the data. We've heard so much about quality controlling of data, cleaning, calibrating. The data we got to from the local sensors were already calibrated by the manufacturer. So we did our own internal checks. And then at the end of the day, we do some validation and we evaluated the model against the ground-based, how it's performing, to be able to inform whether there's indeed some bias and that needs to be corrected. Before then, after the validation, we applied the machine learning to the extreme gradient boosting tool, and we chose the XG boost based on the paper or the work done by Christoph, the link I showed earlier in the previous slide. And so the XG boost had worked well for the global correction of the global forecast, and so we thought it wise to use that. And it's also, I just need to highlight that this work is in collaboration with the developers of the model, Christoph and then his team. At the end of the day, we evaluate the forecast, the bias-corrected forecast we've gotten over these areas. We seek to obtain a robust forecast for 5 days over these pilot cities, and then we re-evaluate the outputs, the forecast, again with the observed. But here, we introduce new data sets to check whether there's been some improvement in the accuracy of PM prediction over the selected cities. The performance metrics, please don't ask me on the RR squared. Yesterday, I wanted to know myself. These are the metrics we looked at. For some results, over Accra, Kampala, Nairobi, and Kigali, we could see that the model is able to predict the trend, the linear trend over this area. However, there's bias, it's underestimated clearly over Kigali, Kampala, Nairobi. It's so clear. The model is represented in blue, The corrected forecast is in red. That's with the, when we apply the machine learning to the GEOS data, the raw data. The raw data is in blue, and the observation is in black. And we could see from here that after applying the machine learning, there was great improvement in simulating exactly what's on ground, the observed data. And this is seen clearly here on the scatter plots, where we could see there's clear underestimation by at all the sites by the GEOS model. On the left panel, that's where we find the raw data against the observed before we apply the machine learning, with the exception of Accra, where the model was able to simulate what the large-scale dynamics with regards to meteorology and climate over the particular area. And also, I need to elaborate that the data we got, it was the grid size, that's the 25 by 25 kilometers square, but then with the observation data, we couldn't get that spatial representation due to lack of data. So it was point source. What we did was extract the point source data out of the 25 by 25 grid cell. And so this machine learning model was designed specifically for that point source, that location specific site, taking into account the environmental conditions over that particular area. And so after we applied the machine learning, we could see that even based on the performance metrics, the MAE and the R-squared, we could see that there was great improvement. MAE reduced by 63.2% over Accra, over Kampala by 73.4%. Nairobi, we see it reducing by 71.4% after applying the machine learning. And then in Kigali, we have about 67% reduction in bias after applying the machine learning to the GEOS forecast. output. Now, here are some key points. It's worth noting that the machine learning model was designed specifically or developed specifically for each site, taking into account the local environmental factors and then also emission at each of the sites. So we don't train one model for all the, we don't apply one correction factor for all the sites or train one model for all the sites. However, the specific model trained for each site because of varying environmental conditions. And then we could see from the results that the model, okay. We could see that the model performed well in Accra, likely due to its ability to capture large-scale dynamics. Differences in local meteorology played key role in the model accuracy over Kigali and Kampala, where we use the local sensor. And also, worthy to know that the bias-corrected model output show strong alignment or correlation with observed data, demonstrating the effectiveness of the machine learning approach in enhancing or improving air quality forecast for any air quality management system. Okay, so here are some summary points. We've seen that applying the SG Boost model significantly improved the accuracy of PM 2.5. The machine learning was tailored specifically for each site and taking into account the conditions over that particular area, which helped improve the forecast. And also, there's the need for regular retraining with up-to-date data, which is essential in maintaining the accuracy based on the environmental conditions that change over time. And also, the last point is improved PM 2.5 predictions are crucial for better air quality management, especially in regions with limited monitoring infrastructure, such as the sub-Saharan Africa, where I am coming from. Now, at the end of the day, we seek to work together with stakeholders, policymakers, to use this tool to make informed decisions with regards to air quality management. Here are the collaborators on the project. Thank you to all collaborators and also the co-authors on the paper I just submitted. Thank you very much for your attention, and that's my email address.
Thank you, Victoria. I used to run WRI's global air quality program, and was around for the beginning of this project, so it's incredibly satisfying to see this kind of presentation coming out in a venue like this. So we've had a very wide-ranging panel across scales, across types of information, across applications. Two key points, I think, came out. One is that constellations of information, so bringing together information from different sources, can be very powerful for creating important and policy-relevant, action-relevant insights. And second, with that in mind, keeping an eye on purpose is essential. That point came out most strongly in Jason's presentation, but I think across all of them, making sure that the constellation is fit for purpose is important. We have officially 8 minutes for questions, but if there are a lot of them, I'm just going to arbitrarily claim 7 minutes, 5 minutes back to open it up to the audience for questions for the panelists. Questions? Raise your hand. And I think actually, so Carl is online, and I believe it's 1 o'clock in the morning if he's in the East Coast US time zone. So out of respect for Carl and being able to hear us, if people can use the mic. Do we have someone who can take a mic around? All right, great. So we have the 2 mic people standing up. Questions? I'm holding time for you guys. I see a question from the man in the red shirt.
All right, are we on? Maybe? Okay, so I have a question for Sarath about sort of local scale sources. So in Kampala, it seems like there are a lot of small scale brick kilns, and other sort of small sources like that. So could you comment on, how do you incorporate those? How do you account for those? And, other than sort of making a best guess.
Hi, thank you. I think it's part of the same, the grid scanning that we do for the city. Once the airshed is defined, for every grid we go, every kilometer we look at it and then find out if there are any sources that are not usually identified. So the same way, the quarries are identified the same way. So we were able to map out about 3.5 square kilometers of those quarries spread across the airshed. The similar way, we found out a lot of those small-scale industries, big industries. What I showed you is only the big industries. And similarly, we have brick kilns also as a separate layer. So on the Zenedo, all the KML files have been uploaded, so you can also use it. So once we have the layer, we put in an emission factor and then put it into the inventory.
And if you could also introduce yourself before you ask the question, please.
Yeah, hi, I'm Ritesh. I work for WRI, and nice to see you, Jessica. So I have a question for Sarath. So I just wanted to understand for the African continental, I just wanted to understand, have you used the local emission factors or used the international emission factors, or
Excellent question. All the emission factors are borrowed. We were not doing any physical emission factor tests in any of these places. So this is a first cut understanding of if there is a cement plant and if they are making 1 million tons of cement every year, looking at the technology in place, looking at the fuel in place, we put an emission factor and then get an emission rate. So that's the thing. In the second round, the cities can then take this forward and say, okay, they can question the inventory. And they basically said, okay, let me just go to the inventory, to go to the cement plant and find out if the emission rate is this or not. I think situation like that, Jason comes into play, and then they can ask him to put up the monitors and find that exact number. So far, all the inventories that we do are using average emission factors that we can, at least they're the best guesses, yeah.
Any other questions, especially for anyone other than Sharath there?
Yeah, hi, this is Brito from Avu, from Chennai. So we are again one of the manufacturers of air quality monitors, especially in indoor. So my question is to Jason. So like a couple of months back, one of our automobile company approached us for gas leak detection of methane. Okay, and then we just deep dived into the industrial monitoring space, but then we thought it was not our cup of tea for the simple reason which you highlighted, that it is all about the certifications and the norms are completely different. And there are traditional monitors available in the market, especially the methane gas detectors, roughly about half a meter or a 1 meter height from the ground. It is being deployed to detect. So how do you think the change is happening with the automobile or the ONG spaces, that monitoring air quality or other gases through LCS sensors, and what is the trend, and what are the customers' mindset or the norms and regulations are there in the industrial space? Thank you.
Hi, is this on? Okay, great. It's an interesting trend, right? Because I think traditionally, if you look at gas monitoring in industrial plants or in an industrial setting, it's typically for safety, right? So they're primarily making sure that equipment doesn't explode and people aren't harmed, right? I think, at least in the United States, in the past few years, there's been a really interesting trend towards the idea that emissions is just as important as safety, right? In that there is real impact to emissions occurring. And I think, a lot of the plants now are starting to understand that, hey, we want to be safe, but we also want to make sure that we're not emitting as much. And what are the simple things we can do, right, to reduce our emissions by a significant amount. And so I think that's really the big shift, right, in terms of people's thinking, is to start to really prioritize emissions on the level of safety, as opposed to before it was like, okay, as long as we keep things safe, it should be just fine, right? So it's a slow-moving process of people's minds changing, but I think it is actually occurring. And so in that sense, safety monitors are typically much higher in concentration. So we're seeing a lot more interest in, ppm level, sub-ppm level detection of a lot of these emission pollutants. Does that answer your question? Perfect.
My question is directed to Dr. Sarath. Thank you very much for the great work you are doing in East Africa. So based on your experience, looking at the kind of vehicles that we have in the East Africa region, second-hand, used vehicles imported into the countries, I don't know whether it is you who said that our vehicles, some of them are in the Euro 1 and Euro 2. Now my question comes on the use of emission factors from other regions. Because you find the emission factors like from US and other parts of the world are developed on vehicles that are in the series of Euro 5, Euro 6. So in your opinion, which one is the most applicable emission factors, or the most appropriate or most similar for application in our countries?
Again, as I said, we borrow these numbers, but we do keep in mind the fleet mix that's actually on the road. For example, you look at the second-hand market, what kind of vehicles are coming in? So there are a lot of vehicles coming in which are already 10 to 12 years old. They ran for 10 to 12 years old in Europe, in UK, and in US, and they're coming into the market. And if they've already run for like 5 more years or 6 more years in the country, so we will adjust those numbers when we have some methods in madness. You can actually look at some of those tools on our website on how to apply deterioration rates on engines to course correct. Exactly way Victoria has shown, you can bias correct these numbers. Same way, we have some methodologies in place to bias correct for emission factors as well, so that what we are putting in the model reflects what we also see on the ground. So it's a give and take, and I can show you some of these things offline. Yeah.
So we're at the end of the session time. If anyone has a question for Carl, who is still online, raise your hand. All right. Does anyone have a question for Victoria? All right, then I will not steal time from the next session. I'll just indicate that, I'm quite pleased to see all the attention to the origins of pollution and the questions on emission inventories. But at the same time, also, the panelists who are here will be here for some time. So if you have additional questions about their presentation or their work or the constellations that they've put together, please do feel free to find them. I'm volunteering them to answer further questions during the breaks and so on. With that, I'll close and turn over the floor to Swagat for a special address. But thank you all, and thank you very, very much to the panelists for taking the time to talk through what they're doing. It's always great to see the very specific applications, constellations, and the many different ways in which these data can be applied to motivate and guide changes that lead to cleaner air. So thank you.